My name is Yoshihiro Ito. I'm an associate professor at the Research Center for Earthquake Hazards, specializing in marine earthquake seismology. Our research center is part of the Disaster Prevention Research Institute of Kyoto University. As a researcher, I'm mainly interested in unraveling the intricate physical mechanisms governing slow earthquakes. Slow earthquakes are an immensely intriguing topic with the field of earthquake seismology, involving unique seismic events. Researchers began to investigate slow earthquakes as late as the early 21st century. Therefore, we are not yet fully able to comprehend their essence encompassing both the physical process at play and subsurface conditions that foster these slow and fast rupture process unfolds. My endeavor to decipher the enigma of slow earthquakes, particularly in the shallow segments of subduction zones, have led to the strategic deployment of ocean bottom instruments across diverse subduction systems, from Mexico to New Zealand and my homeland Japan. Data collected by these instruments serve as a foundation for meticulously charting the spatial and temporal intricacy of slow earthquakes. At the same time, I'm engaged deciphering the subterranean seismic structures, including seismic velocity, density, and porosity from these datasets to unearth the structural underpinnings governing the initiation of slow earthquakes. Earthquakes usually occur when there is a slip in the faults at the ground beneath the surface. There are two types of earthquakes: regular and slow earthquakes. A regular earthquake occurs when a fault moves suddenly and rapidly, causing intense shaking. However, in the case of slow earthquakes, the fault moves gradually, creating minimal ground shaking. What is fascinating is that even if a slow earthquake has the same strength as a regular magnitude 7 earthquake, most people will not realize its occurrence. Why? Slow earthquakes release only a small amount of seismic energy from a fault, and the entire rupture process can stretch over weeks. Slow earthquakes are detected predominantly in subduction zones. A notable instance was observed in the vicinity of the 2011 Tohoku Oki earthquakes. Interestingly, the slow earthquakes occurred before the main event. The events leading to the main earthquakes began with the slow earthquake rupture, whose onset was in late January 2011. This gradual rupture persisted for more than 1 month, ultimately setting off a sequence of events in spring. On the 9th of March, the largest foreshock occurred, followed by the main shock on the 11th of March, making a significant seismic sequence. The movement of tectonic plates is a driving force behind both regular and slow earthquakes, leading to their frequent occurrence along the boundaries where these plates interact. Subduction systems are often located beneath the ocean surface. Advancements in the seafloor technology and instrumentation techniques have enabled us to position instruments on the ocean floor. Using these ocean bottom instruments, we successfully identified instances of slow earthquakes occurring near the shallow plate boundary beneath the sea. Starting in 2017, our attention was directed toward a specific section of the Mexican subduction zone, located off the coast of the state of Guerrero. This region is referred to as the Guerrero seismic gap. Interestingly, within this gap, there has been an absence of significant earthquakes for the past century. When a seismic gap is encountered, two contrasting narratives are open to account for its presence. On the one hand, there is a strong likelihood of a megathrust earthquake occurring, with substantial seismic coupling of Guerrero. On the other hand, there is a scenario in which the potential for megathrust event is considerably diminished owing to notable low seismic coupling, possibly due to the occurrence of frequent slow earthquakes. As we anticipate the possibility of slow earthquakes in the Guerrero seismic gap, we strategically deployed ocean bottom instruments, including seismometers and bottom pressure recorders. Seismometers are adapted at detecting even slight vibration on the ocean floor that arise from both small, slow, and regular earthquakes. In contrast, ocean bottom pressure recorders are equipped to capture vertical displacement stemming from both significant slow and regular events. By analyzing the data collected by the ocean bottom seismic and geodetic networks, we successfully pinpointed the presence of small, slow earthquakes within the confines of the greater seismic gap. These findings indicate a diminished likelihood of the significant seismic event occurring within the greater seismic gap in the future. This is attributed to the fact that strain energy is systematically released during the occurrence of these small, slow earthquakes. As part of international collaborative research effort in New Zealand, we deployed ocean bottom pressure recorders. These instruments were employed to measure variation in the uplift over subsidence of the seabed, which are indicative of the occurrence of slow earthquakes. Although previous research efforts have verified the presence of slow earthquakes in the Hikurangi subduction margin, a gap in our understanding regarding the exact locations of these events. Although previous research efforts have verified the presence of slow earthquakes in Hikurangi subduction margin, a gap in our understanding regarding the exact location of these events remains, particularly of those occurring further from the coastline, such as near the trench. By establishing the ocean bottom geodesy network, we were able to shed light on this matter. Our observations revealed an expansion of slow earthquakes area towards the vicinity of the trench. This observation implies the intriguing possible that these slow earthquakes occur at extremely shallow depths, a discovery that significantly enhances our understanding of their dynamics. Understanding the subsurface seismic structure plays a pivotal role in unraveling the complexity of slow earthquakes physics. In pursuit of this understanding, we have employed advanced seismological techniques to decipher the intricate structural makeup beneath the Earth's surface thoroughly. In pursuit of this understanding, we have employed advanced seismological technique to decipher the intricate structural makeup beneath the Earth's surface, utilizing a combination of offshore and onshore seismograms. A significant milestone has been achieved through the application of the horizontal to vertical spectrum technique to analyze ambient noise captured by the ocean bottom seismometers. This groundbreaking approach has enabled us to successfully drive the velocity of both P and S waves, allowing us to map the structural composition from the seabed to depths spanning several kilometers. Remarkable, this represents the world in angular utilizing of the horizontal to vertical spectrum technique for deep sea seismograms. Our exploration extends further as we have managed to integrate the intrication between the ocean and solid Earth into our calculations. This was achieved by harnessing ambient data collected at the ocean floor using both ocean bottom seismometers and pressure recorders. This innovative approach enhanced our ability to comprehend the intricate dynamics at play beneath the ocean and seabed, that is, the fluid and solid Earth parts. Our research center is actively engaged in pursuing the significant scientific objective, comprehending the intricacies of slow earthquakes and harnessing this understanding to mitigate the potential disasters caused by earthquakes and tsunamis within subduction system. In our relentless persisting of these goals, we employ a diverse array of techniques to shed light on the range of scientific inquiries. Our methodologies encompasses not only seismological and geodetic techniques, but also laboratory experiments and numerical simulations. One of our central focal points is to delve into the fundamental scientific question of how fluid and solid Earth interact within these intricate processes. This exploration derived our quest to unveil the underlying mechanics governing these complex phenomena. Within Disaster Prevention Research Institute of Kyoto University, We have embarked on collaborative projects that cut across interdisciplinary boundaries. Through these collaborations, we strive to develop strategies that can effectively mitigate the potential devastation caused by the earthquake and tsunami. These collaborative approaches reinforce our commitment to advance both the scientific understanding and the practical application for disaster prevention and mitigation.
Hi guys, why do you choose to study at Kyoto University?
For me, the reason I come here to study geophysics is the first is that Kyoto University is very famous around the world, and the second is that I want to study geophysics and I'm interested in it, and Ida Sensei is a top researcher about the geophysics, especially in slow earthquakes. So I choose the Kyoto University to study geophysics.
Around the world, Japan is a reference in seismology. Ito Sensei is internationally recognized as a great science, and Kyoto University is one of the best universities in Japan. For the reason I choose this university. Our group has given me the opportunity to understand different realities of each countries, Bangladesh, China, or Japan. But what is your experience in Ito groups, Faraji?
My experience is very good because this is a very diversified group from many parts, people from many parts of the world active in research, and we do lots of discussions about our research problems, and we do generate lots of new ideas from these discussions, and also we help each other for our issues in our real life problems.
For me, the good point about being in this lab is that I have a chance of doing discussion with very wide variety of cultural and academic background people. So from daily life, I have colleagues from China, Mexico, Bangladesh. I also have Filipinos researchers, and I can discuss with those guys from daily life. So that is very good point about it.
Everyone have helped me about study and my life.
What is your future plan after finishing the academic course here? And what is the possible contribution probably you can make to your home country with the specialties you learn in these Kyoto universities?
Ultimate or very near future goal is to go back to my country and join my old job, and also the other long-term goal are to continue study seismology, and also to propagate the knowledge I obtained here to the others in my country.
For the long term, I think that because I come from China, China is similar to Japan, and there are also many earthquakes. So but for my research now is the slow earthquakes. There are less research in China.
I want to be a teacher in Chinese university.
We look forward to understanding the nature of both slow and regular earthquakes with you. Our research is fundamental for mitigating future destructive disasters caused by earthquake and tsunami in the country. Would you like to join our research center and join the science at the Kyoto University?